I'll put this up at the end too, so you don't need to copy it now. It'll be on the website. It'll be emailed, everything. I'll put it up at the end. I don't think this will take all class. Okay, so let's see, blue. Switch to blue. Right, so I'm just going each set of problems in the study guide. Right, so now I'm on page 12, 7 through 10. Right, and if you have a hard time seeing it, just go to page 12, 7 through 10 and look at it. But sets of numbers, right? What kind of number, what sets do each of these numbers fall into? For example, in the number 7, right, which of those numbers as you look across is a irrational number? How do you recognize irrational numbers? It's kind of, okay, as a decimal, they don't terminate and they don't repeat, right? And so, I mean, this number 9 is trying to show a decimal that it does not appear that it terminates because it's got ... at the end, and it doesn't look like it's repeating because they keep changing what follows, right? 0.01, 011, 0111, right? But it doesn't just take the same thing and keep repeating it after. So that's an irrational number right there, right? Okay, what is another way that we usually give examples of irrational? This square roots that can't be simplified, like the square root of 2, that's an irrational number. And what's the other one that we use a lot? Pi. So let's see. I don't see a straight up pi, but I see a 1/2 pi. Would that be irrational? Sure. You know, if pi is irrational, then half of pi is irrational. So those are irrational numbers. What about in this first list here? Just let's take 2. What are the sets that 2 falls into? Out of the natural, whole, integers, rational, and irrational, what are the sets that 2 falls into? All but irrational, right? 2 is a natural number, meaning it's a counting number. It's a whole number because that includes all the natural numbers. It's an integer, and it's rational because you could write it as a fraction if you put it over 1. Right? What about 0? Which sets would that be in? Yeah, it won't be a natural, right? Natural does not include 0, but whole includes all the natural numbers plus 0. Okay, what about -4? Is it a whole number? What is it? It's an integer, right? Integers are the whole numbers plus and minus, right? And then what about, fractions or rational numbers? You should know that. Okay, so sets of numbers. There's going to be something where you evaluate an absolute value. So do we understand, for example, the absolute value of -10 is +10, right? The absolute value of 0 is 0. The absolute value of, they don't have any positives, but what if I had the absolute value of +10? It would still be 10, right? Absolute value turns everything positive. Do you remember when we did these things here? What do you get if you divide the absolute value of an expression by the expression? I mean, in this case, you're either going to get 1 or -1, right? For certain x values, this will be the opposite of this, and you get -1. That's why they got this x less than -2. If you plugged in, let's say -3, you'll get -3 plus 2 is -1. Absolute value is 1. But the denominator doesn't have the absolute value. It's still -1. 1 over -1, -1. What if x was 0? Then you'd have 2 over 2, 1. So these have their own unique shape. If we graph them, they look like, up to a point, they look like 1. After a point, they look like -1. But I believe the main point of the question, when you see it, is going to be more like these questions here. Right? Can you evaluate an absolute value? Properties. right? In your book, they call these the basic rules of algebra, but up till this year and up till this book, we've always just called them properties, right? Properties of real numbers. Things like commutative for multiplication and addition, associative for multiplication and addition, distributive, right? I mean, we've seen these properties many, many, many times. Trying to remember if this was class. I don't remember if I mentioned this last time with that property. I don't think so. I think I talked about this in pre-cal. We was getting ready because they had also some questions about properties. All this emphasis on properties and set notations and things like that, all that came up in the 1960s as a reaction to, if you've ever in a history class studied Sputnik. Do you remember ever hearing Sputnik? What was Sputnik? Yeah, it was a Soviet satellite that in 1957 they were able to successfully orbit a satellite around the Earth. That was the first time. That meant we had them flying right overhead, and the country freaked out. Much worse than Ebola, okay? Much, much worse. We were like, oh my gosh, they're going to drop bombs on us from up there. And so there became, that's when we started putting a lot of emphasis in math and science and the space program. At the time, when they tried to revamp the math curriculum, they didn't have somebody that was they don't have a government agency that writes math curriculum. So they went to a bunch of mathematicians who came up with some pretty cosmic ways to learn math. For example, teaching addition as being the union of the number of items in two sets. I mean, it seems convoluted, but that's the way they taught math in the 1960s. And it was called the new math. And the thing is that parents were really upset when their kids came home with their stuff. They're like, what did you do? I don't understand any of this stuff. How can I help if I don't understand it? And so that phased out pretty quickly after the 1960s. But it's kind of a legacy of all that we teach all these properties all the time. I don't think that we used to put so much emphasis on commutative property and whatever else, additive inverse and multiplicative identities and things like that. Okay, can we plot points in the coordinate plane, right? Do we know where in the coordinate plane x is positive, right? Where, if we number the quadrants, right? 1, 2, 3, 4, which two quadrants is x positive, right? 1 and 4, x is positive, right? Because that's telling you to the right. And which quadrants are negative? 2 and 3, right? Where is y positive? Right, 1 and 2, right above the middle. Where is x positive or y negative? 3 and 4. Okay, where, this is the important part, where does y equal 0? Y equals 0 on the y-axis? On the x-axis, right? Everywhere on the x-axis, y equals 0. Where is x equals 0? On the y-axis, right? That's important to know. Okay, so these are all just some kind of exercises in that. I think these are probably the ones at the bottom that are the most challenging, bit like where is x positive and y negative? I mean, based on what we just said, where would x have been positive and y negative? 4. X is positive, y is negative, 4. Whereas x equals negative 4 and y is positive, right? So x equals negative 4 puts you over here, but y is positive 2. X is less than 0, that puts us over here. Negative y is greater than 0. Well, if negative y is greater than 0, then y is less than 0. So it's quadrant 3. And if a product is positive, the product xy, then which quadrant are you in? Well, definitely 1, because they're both positive. You multiply them, you get a positive. Which other quadrant? 3, because they're both negative. Negative times negative, right? So the product is positive, positive. Okay. So know your quadrants, how x and y change. Where is x 0? Where is y 0? And that leads right to this. right? How do you find the x-intercept? Set y equals 0, right? So to find the x-intercept, right, set y equals 0, solve for x. Right, to find the y-intercept, set x equals 0, solve for y. Right, so for example, let's say we went to, let's do 54, right? Right, to find the x-intercept, I set y equals 0, right? So that would give me 0 equals the square root of 2x minus 1, right? Solve for x. Square both sides. What's the square of 0? 0. So 0 equals 2x minus 1. 2x equals 1. X equals a half. That's the x-intercept, so the point is 1/2 0. For the y-intercept, set x equal to 0. Okay, what happens in this one when you set x equal to 0? Y equals the square root of 2 times 0 minus 1. Y equals the square root of negative 1. What does that tell you? What kind of number is that? It's imaginary. Square root of negative 1 is imaginary, which means it doesn't cross the y-axis. There is none. Right, but just remember these steps. Good. Okay. Okay, how is it that we come up with the equation of a line when we know one point and the slope? What form of a line do we use? No. Point slope, right? Point slope, which is y minus y1 equals m times x minus x1. Okay, now, if the goal is to put it into slope-intercept form, right, if you're trying to go from there to here, y equals mx plus b, then you might notice, for example, on number 43, that you have a slope and you have a point, but that's just not any point because x equals 0, that is the y-intercept. It is the y-intercept. So actually you have all you need to just go right to there. Right? That would have been 3x minus 2. You know, you could go here and solve, but you should get that. If you don't have the y-intercept, then you'd have to put it into this and solve. Okay. What kind of lines are these lines at the bottom here? These are the ones that we definitely should know. I mean, those two slopes we confuse sometimes, right? Undefined and 0, right? What kind of a line has a slope of 0? Horizontal line has a slope of 0, right? Because it goes like this, right? We know that that's a positive slope, and we know that that's a negative slope. So right in between positive and negative, that's the 0. Okay. How do you make the equation of a horizontal line? It's y equals, right? It's whatever that is, right? In this case, it could be y equals 3, right? Because every point on that line has a y coordinate of 3. So y equals 3. So for this one right here, where it's at 53, it says, find the equation of a line that has a slope of 0, and it goes through the point 4, 5 halves. I think that's a 5, isn't it? Let's say it is. what would be the equation of the line? Y equals 5/2. It goes through y, that y point, so it's got to have y equals 5/2. Every point on that line must have that same y coordinate. Okay, what about the undefined? That's the vertical line, right? And a vertical line has the same x coordinate for every point on the line. So its x equals whatever that number is. So let's say on number 51, what would be the equation of the line? X equals 6. How about number 52? X equals -10. Right? So whatever the x coordinate of that point is, that has to be it. Okay. So this one is x equals -10. This one is x equals 6. Right? This one was y equals 5/2. I mean, I'll give you that same little buck slip of the formulas for those 5 things, right? We had, even though they're not all on here, there's no distance or midpoint on this. But still, if it helps you to have point slope or slope formula. Okay, parallel and perpendicular lines. We just have to know, and that's why I direct you to these problems in particular, but what do we know about the slopes of parallel lines? They are the same, right? I mean, if you have 2 lines that never intersect, then they must be going up and over exactly the same. Rise over the run is exactly the same. So parallel lines have same slope. Okay, so which out of these 4 problems are parallel? $65. Okay, let's see. 1/3, 1/3. So these are parallel. PA for parallel. 66, 4x, 4x, parallel. Okay. Okay, now, what about the slopes of perpendicular lines? Okay, I'll just tell you, one of these is perpendicular and one of them is not. Which is the one that's perpendicular? 68 is the perpendicular because the slopes are opposite sign, flip the fraction, right? So -4 of this, +5/4, that's perpendicular, PE. Okay. And what about this one? Is it parallel? Is it perpendicular? No, that's the neither, right? So this is neither. So just remember what we're supposed to know about parallel and perpendicular lines. Functions. How do you tell in any of these formats whether or not you're dealing with a function? Like in a table of, or a mapping diagram like this, what do you look for? Not quite. That's what you're going to do when you come here or here. What are you looking for in these? Something like this means not a function. If you got 2 arrows coming from the same x, that's like the x repeating in one of these. So this is not. Right? This is a function because you don't have 2 arrows coming from the same. It does not matter that two x values go to the same y. That's okay. That's a function. Right? And when you're looking at tables of values, you're looking for repeats. Right? So what would you say about number 7? No, because it's got repeated 7s. Number 8, you would say yes. And the same thing here, right? Look for repeated x values. What do you look for in an equation? Y squared or any even power of y would say not a function. So when we looked at the number 11, you say not, right? Because that's squared, not. Okay, how about number 12? That's a function because it's y to the first. How about number 13? That's a function, right? Still y to the first. Number 14? Not. Okay. So just remember how as we look at an equation and tell that. Okay. What do we call these things? Piecewise defined functions, right? Piecewise meaning each piece of the domain has a slightly different definition for the function. How do you evaluate a piecewise function? Let's say in the first one here, how would I find f of 2? Okay, you're going to look at these two domains. These are the pieces of the domain. Is the 2 in the piece which is x less than 0, or is the 2 in the piece which is greater than or equal to 0? It's greater than or equal to 0, so you're going to use that one, right? You're going to use that. So that would be 2 times 2 plus 2, 6. Right? But what if I was going to use f of negative 1? Negative 1 is less than 0, so you would be using that function. 2 times negative 1 plus 1, negative 1. So there would be an evaluate like that, and it's that simple, right? Just pick the right piece of the domain, plug into that one. Since it's multiple choice, you won't, they're not going to give you 2 answers. Like sometimes you guys will like fill in all of them to get answers. That won't happen. Okay, domain of a function. So remember, at this point in the class, as far as domain goes, there's 3 possibilities. Either it's all real numbers, or it's limited because of divide by zeros, or it's limited because of square roots or even roots, because we can only take square roots or even roots of positive. So when you look at like number 49 and number 50, right, there's no dividing, there's no square roots, all real numbers, right? That's all you have to worry about, all real numbers, all reals. Right. When you look at problems like 51 and 52, you've got the dividing by an algebraic expression or a variable expression which could equal 0. So you need to restrict those values of x. Okay, so in this case, the value that t cannot have is 0, right? You'd say t does not equal 0 because that would make you divide by 0. And what would you say over here? Y does not equal negative 5, right? Okay, now pay attention to this one because I just tell you that this test, which I've gleaned from things that they've made me use, okay, the way they say it for that exact kind of problem, they say, find the x value where the function is discontinuous. 0, negative 5. Because if you looked at the graph, something like t, that would look like this. So the graph is discontinuous across x equals 0. If you drew it, you'd have to go like that, then you'd pick up your pen, you'd go like that. So just be aware of that language. And then how do you find the domain when it's a square root? How do we make sure that we are taking the square root of positive numbers or 0? Set what's inside greater than or equal to 0, right? So take this one, for example. Y minus 10 is greater than or equal to 0, right? Solve that for y and you'll have the domain, right? Y is greater than or equal to 10. What about 54? This one is a cubed root. Do we have the same issue? Now you can take the cubed root of a negative number. So x, that's all real numbers. Like that, because of this, all reals. Okay. The purpose of this graph, these problems, again, which were the closest I could find to something that would help you for this test, was domain and range. It was not about the part where find the indicated function values. It was about the domain and range, right? Can we look at a graph and estimate a domain and range? For example, in this graph right here, right, if we assume these arrows go on forever, up and to the left and right, then the domain is all real numbers. But the range is not all real numbers because it clearly does not go infinitely up and down. So we would say the range is, how far down does it go? About -4. So you could say y is greater than -4 or greater than or equal to. And remember, the way to say that, again, I'm sure that they've used the notation. We would always say y greater than or equal to -4, let's say. They would say, sorry, I need to undo that. Edit, undo. -4, comma, infinity. With the interval notation like that. From -4 to infinity. What about a function like that, where that's going infinitely down and infinitely to the left, and that's going infinitely up and infinitely to the right? What is the domain? All real numbers. How about up and down? All real numbers. Looks like it goes on forever. What does it look like the domain is of a circle? Is it all real numbers? Right. What's the least x value you see on that? Yeah, it looks like the circle has a radius of 5, right? So the domain is -5 less than or equal to x less than or equal to 5. And it looks like the range is the same way, -5 to 5. I put this one on here because I think that the very question that says something about the value, put it in your calculator and see which is the value for which the function is discontinuous. It's like that. You know, if you're looking at that, you would say, look, where does the graph switch? It's at x equals 0. Now, if you put it in your calculator to do that, to look at the graph, how else could you tell where it's discontinuous? Look in your table of values, see where it says error. Right? If you put it in there and then you're looking at the table and there's one value that has an error, you've got it. That's it. Okay. And you understand the concept of finding zeros graphically. How does that work? Yeah, if it touches or crosses the x-axis, that's a 0. So graph it, look for the zeros. 15. Okay, remember the increasing and decreasing. For example, what is this function doing here? Increasing, right? How would you state that? What's the interval that it's increasing? -infinity to +infinity, right? They're x values. Okay, what about this function? What is it doing from here to here? Decrease, and how would you state that interval? -infinity to 2, the x value, not the y value, the x value. And then what's this interval? 2 to infinity. Okay, so there'll be that. I'm sure there's one where they're going to give you the graph. There's another that says put it in your calculator and then estimate it from what you're seeing in the calculator. Okay, I think there's 2 like that. 16. And that's why I put this section up too. So there was one that had the graph, and we did it from the graph, and then these, put in your calculator and do the same thing. Okay, understand how do we shift things around? What were all the things we did to transform a graph? Let's say on this absolute value function, right? They're saying use the graph of f of x equals the absolute value of x, right? Here's all the things that we could do to a function like that. Right? We could multiply it by a number outside the absolute value. We could add or subtract a number inside the absolute value, and we could add a number afterwards. So what were all the effects of these things? What does it do to the graph when you add or subtract inside the function? Which kind of a shift is it? Inside, minus means right, plus means left. Okay. Outside, vertical. Plus means up, minus means down. Okay. What does the A do to it? If you multiplied, if we had something like f of x equals 2x, do you remember what was the transformation that we called that? I mean, it literally takes it takes the V and it makes it look more like that. What did we call that? It's a stretch, right? That's a vertical stretch by a factor of 2. Okay, what did we call it when it was 1/2 x? It's a shrink or a compression, either one of those. I mean, let's say if you had to write an equation for this and you really weren't sure what you were doing, let's say you write your equation, then put it in the calculator and see if it looks right. Right? Maybe if you've got the, what does it do when I add or subtract inside, you know, is it left? Does minus mean left or does it mean right? Just try it. Put it in the calculator and see which way it goes. It won't take you too long to figure out. So you need to understand the shifts. If you're looking at a graph, come up with the equation. Or if you're just told, you know, okay, here's the parent function, write the equation that would shift it 3 units right and 7 units down. Okay, starting with x squared, how would I write a function which is 3 units to the right? How would I write that? Inside would be x minus 3, and then 7 units down, minus 7, like that. Let's see if they have one which is I'm seeing if there's any stretches or shrinks, but I don't see that. What is it? How do we reflect in the x-axis using that terminology? So I wanted to show f of x reflected in the x-axis. I would put a minus in front, right? Flip it. You might call it a flip, but they're going to call it reflect in the x-axis. So know how to do that. 19. Okay, on the study guide, it says A and B for these problems, meaning that the problem you've got is either a add or a subtract. It's not one of the multiply or divide with a domain on it, right? So when you're practicing these, don't worry about those last couple, right? It's either the A or the B. So how is it that we add functions? F plus G of x means f of x plus g of x, right? And how do you do that? You just replace the f of x with what it equals, and you replace the g of x with what it equals. Simplify, right? So remember how to do that. I think that the reason that I put this on was because there is going to be a problem where you're giving f of x and g of x, and you're told to do something like find f of g of 4. So remember how we do that? We write it like f of g of 4, and then what? Find g of 4, right? So g of 4 in this case is 0, and you put that in the place of the g of 4, and now you do f of 0, which is 4. So remember how to do that process. You won't have graphs for it. You'll have 2 definitions of functions. So you just plug into one, then plug into the other. Okay, then this stuff which we just did in the homework. Okay, now there's a reason why I didn't put the compositions and the inverses, which were part of the P chapter, on that last test. Because honestly, if I put them on problems like this, it's just going to bring people's grades down. On this test, which is multiple choice, when you get to the inverse problem, on a multiple choice question about find the inverse, remember, you got a really easy strategy to figure out which is the inverse. If you don't remember the whole process, then look at this problem right here. Determine whether this function right here has an inverse, is 1-to-1, sorry, because that's the way it'll be worded on the test. And if it does, find the inverse. So how do we determine whether it's 1-to-1? Graph it. And which test does it have to? Horizontal line test. So you go ahead and you do that. I'll tell you, it passes. This one passes the horizontal line test. Okay, then remember that for the function and its inverse, it must be the case that if I do like f of 0, and I get, in this case, 6 over 3 minus 0, which is 2, then it must be the case for the inverse that F inverse of 2 equals 0. So just check on these here. Which one of these, when you plug in 2, do you get 0? The letter C, right? If you plug in letter C, you get 3 times 2, 6 minus 6 is 0. 0 over 2 is 0. So there's your inverse. So in a multiple choice format, that's how you can find the inverse very quickly. I mean, I wouldn't, even if I was doing it, I wouldn't bother finding the inverse if I could do that check and it gave me a clear answer. Every once in a while, I've seen problems where 2 of them ended up giving the same answer, but that is not going to be your issue on the test, okay? If you can just do that kind of a thing, you know, you'll be able to find that inverse. Okay, then we jump to the part which we did at the very end. We did, remember in the first part, we did sections P1 and P2, which included solving equations. Then we did the complex numbers so that we could solve equations and get imaginary solutions, because up till then we wouldn't be able to deal with that. So when it comes to imaginary numbers, what do we mean by the complex conjugates? Like 9 plus 2i, what's the conjugate? 9 minus 2i, right? You just switch the sign in between. And these problems here say, and then multiply. I don't think that's what you're going to get on the test. It's just going to be a question about conjugates, all right? If you multiply, though, just to show, what do we expect to happen when we multiply these imaginary numbers which are conjugates? What's that? Yeah, what do we expect to happen when we do it? All the i's are going to go away, okay? That's the reason you multiply conjugates, because it get rid of all the i's. 9 times 9 is 81. 9 times negative 2i is minus 18i. 9 times 2i is plus 18i. And then the last 2i times negative 2i is negative 4i squared. But what does I squared equal? Negative 1. Right? Remember, I equals negative. I equals the square root of negative 1, so I squared equals negative 1. So we're going to replace that. Right? These cancel, and now this is 81 plus 4, which is 85. But there's no more i's. That's why you find conjugates. Okay. Okay. And I think this is the last one. Okay, and this came from the, once we knew about the complex numbers, then we could actually solve these polynomial equations and at least figure out the number of real solutions, and we would know what those other solutions are. Okay, so when we look at these functions here, if it says find all the real zeros, what are they asking for? Yeah, you can look at the graph and see where across the x-axis. Okay, so let's take, for example, number 32. How many total zeros does this have? How do you know that? The highest power of x, the degree. The fundamental theorem of algebra says that whatever is the degree, that's how many complex solutions you've got. Now, complex means real or imaginary. Right? So you don't know how many are real, you don't know how many are imaginary. But we would say, because of this, we would say the complex solutions are right? 3. Okay, now to find out how many real solutions, we put it in the calculator. So let's see, x to the third minus 4x squared minus 4x plus 16. And I hit graph. Okay, so how many real solutions are there? 3, okay. So real, 3. Okay, how many imaginary solutions are there? Well, it's got to be 0, right? Because it adds up to 3, and they're all real. right? What if there was one real solution? There'd be two. What if there were two real solutions? Anybody? Remember, imaginary solutions occur in the conjugate pairs. So you always get an even number of imaginary solutions. So in the end, you cannot have two real and one imaginary. You can only have one real and two imaginary. Okay, that's what, remember, they always occur in conjugate pairs. I mean, just think, for example, a cubic function like this. Because it's cubic, we know the shape of the graph. It's going to start, somewhere down here, and then it's going to end up there. It has to cross the x-axis once. There's no way to go from here to there without crossing. So it's got to have the 1, but it doesn't necessarily have to have the 3. It could be that the last two are imaginary, which means you're going to see that little dip above the axis, something like that. But it's cubic, so it's got to cross once. A quartic looks like this, something like that. That could definitely stay above because it's, starts high and it ends high. And it could miss the x-axis altogether. But if it's a cubic, it's got one real solution. The only matter is, does it have 3 or 1? Okay. So there is one question which asks about numbers of zeros. Not to actually find all the zeros, just how many. I think, and the way that it's worded is non-real, right? How many non-real, which means imaginary. And that takes us back to this. So do you have any questions? I mean, I'll be here every day, before and after school, Saturday. The video that I just made, I'll put on the website. If you want to go back and look at it as you're doing the study guide, make sure you're getting everything out of it that you should.